So, yesterday I was explaining you the symbol O. So, in order to understand this symbol, let us consider two functions f and g, which are real valued functions or complex valued also, no problem. These are two real valued functions with the condition that limit of f when x goes to 0 is 0, as well as the limit of g x when x goes to 0 is also 0. So, we try to see the quotient function f upon g. So, consider f x upon g x when the limit x goes to 0. Now, this limit is maybe 0 or it may be infinite also. So, the case when this limit is 0 can be understood because suppose I assume that the limit of f x upon g x when x goes to 0 is 0. Now, this will happen if and only if f approaches to 0 faster than g when x approaches to 0. So, this happens when f approaches to 0 faster than g x when x approaches to 0, when x goes to 0. And this fact is expressed by writing a symbol. So, when box condition holds, we write that f is little o g. So, symbolically this limit equal to 0 is expressed by writing f equal to little o g. As an example, you can think of functions. Suppose f x is x to the power 5 and g x is x square. You can see that the limit of the quotient f upon g when x goes towards 0 is actually x cube, and when x will go to 0, this limit will be 0. So, here I can say symbolically that f is little o g. This symbol you have seen being used in Taylor's formula. So, if f is a differentiable function from R to R, then we know that the derivative of f at a point A is actually f of a plus h minus f of a upon h when h goes to 0. This limit is called the derivative of f at a point A. So, now I can write down this expression as f of a plus h minus f of a minus h times f dash a upon h. In the limiting case, this is 0. So, derivative of f exists at a point A if the limit of this quotient is 0. Now, in our symbolic representation, I will say that this is equivalent to saying that f of a plus h minus f of a minus h times f dash a is o h. Okay. Or I can also rewrite it as, if it is visible to you, f of a plus h is equal to f of a plus h times f dash a plus O h. Now, you can recognize this as a Taylor series. So, if you write down Taylor series up to first order term, then you will see that this O h is actually the remainder term, and whenever Taylor series is convergent, the remainder term tend to 0 faster than h. Okay. Or you can write down h square upon factorial 2 f double dash a plus terms of the order of h square and so on. So, this is the remainder term which tends to 0 faster than h whenever f is differentiable at the point a. All right. Now, this symbol will be used in our subsequent discussion. Okay. So, our primary aim was to define the tangent line. In fact, I am going to work out the equation of the tangent line also, but to do that, first of all we need to understand the idea of contact between two curves. So, suppose I have got two curves C1 and C2. So, contact between two curves So, I am assuming that C1 is R equal to R s. So, this is the parametric equation in natural parameterization for the curve C1 and C2 another curve. Suppose let me write down R1 s, the second curve is R equal to R2 sigma. At S and sigma are the natural parameters of C1 and C2. S and sigma are natural parameters of C1 and C2 respectively. Okay. Suppose they intersect at certain point P, okay, and these two curves are space curves. So, they lie in the space R3. Let me draw the figure over here. Okay. So, these are the two curves, first one is C1, other is C2, and they intersect at a point P, and P I assume has a position vector R 1 S 0. The same point lies on C2. So, suppose it is also R 2 some sigma 0. Okay. Now, I will choose. So, this is the point of intersection. So, let P be the point of intersection, of C1 and C2, of course. Let us choose points say P1 and P2 on C1 and C2 respectively, and I choose this point in such a way that the arc distance from P to P2 is h, as well as the arc distance along C2 from P to P1 is also h. Okay. And then I will consider the distance, straight line distance between P1 and P2. Suppose this distance is d. Okay. So, we say now I am going to define the contact. With all the description in mind, we define the contact of C1 and C2 at a point P. So, C1 two regular curves two regular curves in R3 intersecting at a point P, intersecting at a point P which is R as 0 as well as R 1 as 0 as well as R 2 sigma 0. Two regular curves in R 3 intersecting at a point P are said to have a contact of order n. So, when I say these curves are regular, in fact they are regular of certain class. So, since I am talking about contact of order n, so I must choose these curves, regular curves, regular of class some C n plus 1. Okay. So, one order more than the order of contact. We say that they have a contact of order n at P if what happens, if D equal to order f h to the power n. So, this is the defining condition for the contact between two curves, and you can understand what I mean by writing D equal to O h to the power n. In fact, you know, when P 1 and P 2 tend towards the point P, when h goes to 0 is equivalent to saying that point P 2 tends towards point P as well as P 1 tend towards the point P along their arcs, then D will also tend towards 0. Both quantities h as well as D both will tend towards 0. What I want, that D tend towards 0 faster than h. Okay, this may not happen all the time that D tends towards 0 faster than h to the power n. You can think of curves where this is not happening. So, in order that the curves have a contact of order n, this should happen. If you consider two curves like this, then this point P 1 and P 2 will be too far off. The distance will be far more than that arc distance h. So, in that case D will not tend towards 0 faster than h. So, what I want, they should be nearer to each other. Okay. All right. So, this is what we visualize it. All right. So, this is the meaning of the order of contact. Now, with this definition in mind, I can talk of the tangent line. Tangent line to a space curve. Okay. So, now let me see if there is anything else to be said. Okay, no, before discussing tangent line, I have to find out a characterization. In fact, you may not be able to work out the order of contact between two intersecting curves with the help of the definition itself. So, we need to develop certain characterization. That characterization is given in this theorem. So, two curves, two regular curves, let C1 be r equal to r 1 s and C 2 be r equal to r 2 sigma, be two curves, two regular curves rather, regular curves of class C n plus 1. Be two regular curve of class C n plus 1 and then C 1 intersecting at a point P, intersecting at a point P with P equal to r 1 s 0, which is same as r 2 sigma 0. Then C 1 and C 2, then C 1 and C 2 have a contact of order n at P if and only if this is a characterization. So, if and only if their derivatives of r 1 and r 2 coincide up to order n at the point P, that is r 1 s 0 is same as r 2 sigma 0. This is obviously true, and r 1 dash s 0 should be equal to r 2 dash sigma 0 and so on, and the nth derivative r 1 nth order derivative at s naught is same as nth order derivative of r 2 at sigma 0, and yes, and but r 1 s 0 n plus 1th order derivative, because I have taken regular class C n plus 1, is not equal to r 2 of n plus 1th order derivative at sigma 0. They should not coincide. Okay. If you want exactly order n, then this should not happen. Up to here all the derivatives should be. Slopes in first dash and second dash will also coincide, but it is little higher. It is the same kind of a difference when you say the function is analytic or C infinity. Otherwise, all derivative exists in both cases. So, the tangent will be same, but it is little more deeper, because they touch each other quite closely. Okay. So, this is what we have been demanding. So, let us see the proof of this theorem. So, proof. So, since the curves are regular of class C n, I can write down C n plus 1, I can write down the Taylor series. So, by Taylor's formula, I can expand R 1 S 0 plus H. So, this will be equal to R 1 S 0 plus H times R 1 dash S 0 plus H square upon 2 factorial R 1 double dash S 0 and so on, and then H to the power n upon n factorial R 1 nth derivative as 0, and there will be more terms, and they will be terms of the order of h to the power n. You should understand that from this, after this term, all the term will be of the order of h to the power n. You can see them. Okay. Why? How? You see, in the next term will be h to the power n plus 1 upon n factorial, or 1 n plus 1 at derivative at s 0, and so on. Okay. Now, next will be h to the power n plus 2 r 1 n plus 2th derivative s 0 upon n plus 2 factorial, and so on. Now, h to the power n plus 1 I can take common. Okay. If you take h to the power n plus 1 common from this infinite series, you will be getting r 1 n plus 1 at derivative at s 0 upon n plus 1 factorial, and so on. Now, in order to see whether this is a term of the order of h to the power n or not, so what do? You divide. So, this is the term which I am saying is a term of order h to the power n. So, to confirm it, yes, it is a term of order h to the power n, I will divide this, I will divide whole of this by h to the power n. Okay. So, now you can see this h to the power n will cancel one power, okay. Sorry, n power n will be cancelled out, and h 1 h will stay, and when you will take the limit, it will become 0. Okay. So, that is why I am saying it is a term of the order of h to the power n, and not h to the power n plus 1. The next one will be a term of the order of h to the power n plus 1. Okay. Okay. Similarly, I can write down the Taylor series for the second function r 2 sigma 0 plus h. This will be r 2 sigma 0 plus h times r 2 dash sigma 0 plus h square upon 2 factorial r 2 double dash sigma 0 up to, say, I will write down h to the power n upon n factorial r 2 nth derivative at sigma 0 plus here also terms of the order of h to the power n. All right. Now, one should keep this in mind that these dashes are the derivative with respect to the natural parameter. We have fixed up our convention that the dash stands for the derivative with respect to natural parameter, and the only parameter we have is the natural parameter. All right. Now, let us see the difference. If you recall the figure, you can see what is happening in the figure. Look at the figure once again. These were the two curves, C1 and C2. This is the point P, then you have P1 and P2 here, and these distances are h along their arc, and the distance from P1 to P2 is d. Okay. Now, if you since all these things are happening inside R 3, if I join the point P with the origin, then it will become the position vector OP1 and OP2. So, R1 S0 plus H is actually OP1. Similarly, R2 sigma 0 plus H is OP2. Now, if you subtract 1 from 2. So, R 2 sigma 0 plus h minus R 1 S 0 plus h. This I can see this is R 1 S 0 plus h, this, and this is R 2 sigma 0 plus h. And their difference you can see from the figure is in fact the vector p 1 p 2. When I will take the mod, it will become the actual distance d. So, first let me write down the vector p 1 p 2. So, term I will, since these are vector quantities, I can subtract term by term. So, this is R 2 sigma 0 minus R 1 S 0 plus h, you can take common between these two terms, R 2 dash S sigma 0 minus R 1 dash S 0 plus h square upon 2 factorial R 2 double dash sigma 0 minus R 1 double dash S 0, and so on. We can come up to here. So, h to the power n upon n factorial common, R 2 nth derivative at sigma 0 minus R 1 nth derivative at S 0 plus the difference in the remaining remainder term, but they will be terms of the order of h to the power n. Okay. Now, when you will take the mod, this quantity will also be in the mod sign. Okay. So, the left hand side becomes d and the right side is this mod of this. The remaining terms you can write down. Well, what we are demanding is that this d should be equal to order of h to the power n. This will happen if and only if all the term before this, all terms of the order of h to the power n should separately be equal to 0. Okay. One can get confused that why it is so. If this equal this, then this sum must be 0, not each term equal to 0. This may be a confusing point for you. So, I can explain to you. You see what you have suppose a vector in R n. Okay. So, this vector can be written as a 1, a 2, a 3 and so on, something a n minus 1, and suppose the last one is b. It is a infinite, it has infinite components, but I am writing like this n minus 1 term and nth term is something b, or if you like you can write down d. What I know is that mod of x is d, okay, and mod of x from its component is equal to under root a 1 square plus a 2 square plus so on a n minus 1 square plus d square. This is equal to d squaring both sides. What you will be getting a 1 square plus so on a n minus 1 square plus d square equal to d square. So, what do you see from here is that a 1 square plus a 2 square plus a n minus 1 square are equal to 0. So, you have n minus 1 quantities, the sum of whose square is 0. This is possible only when each of them is 0. So, what do you see is that a 1 square is 0 and therefore, a 1 is 0, a 2 is similarly 0, a 3 is 0, all of them are 0. So, that is what I am going to conclude here, because mod x is this. OP2 minus OP1, R2 sigma 0 plus H minus R1 S0 plus H. Their difference is the vector P1 P2, and the length of this vector is the distance d. Okay. So, we are concerned with d because our definition is given in terms of d. So, d equal to this much. So, if you wish, I can write down all the term here, so that you can see them. So, you have first term in here R 2 sigma 0 minus R 1 S 0 plus H times R 2 dash sigma 0 minus R 1 dash S 0 plus so on H to the power n upon n factorial. What is the term? R 2 nth derivative at sigma 0 minus R 1 nth derivative at S 0. Okay. So, since d equal to if we have assumed that curve have a contact of order h to the power n. So, d is 0, since d equal to order of h to the power n, we must have what we must have? All the terms in this sum must be 0 separately. We must have R 2 sigma 0 is equal to R 1 as 0. Similarly, since h is not 0, what will be 0? Their derivative R 2 dash sigma 0 minus equal to R 1 dash as 0, and up to here you will be getting their derivative are coinciding R 1 nth derivative at S 0. So, two curves have a contact of order h to the power n, have a contact of order n if and only their derivatives up to order n coincide from 0 onward. So, if I have completed 20 minutes, we can check it up. How is the recording going? 30 minutes. Okay.